Okay. Welcome to the second speak this morning. It's a pleasure to introduce Jesús Álvarez from Santiago de Compostela, the University of Santiago de Compostela, and this Galician Center for Mathematical Research and Technology. Well, Jesús works in many things, foliations, but many differential geometry around, including geometric analysis. Well, I think the best is that we listen to him. So his talk today is Zeta invariants of Morse forms.
Thank you very much. Good morning. First, let me thank the organizer for this opportunity, which is a great honor for me. The title is, as the chairman said, Zeta invariants of Morse forms. And this is a joint work with Yuri Korbikov and Eric Leishman. Yuri Korbikov from Russia and Eric from Paris. I will talk a little bit about the motivation of the problem and some the definitions, and then the ideas of the proofs of the main result. So let me talk about the motivation. The motivation is a problem which was proposed by Christopher Denninger. If you have a compact foliated manifold and a foliated flow, which means that it maps leaves to leaves, so it induces an action on some kind of cohomology along the leaves, and he asked how to define a left-shift distribution on the real line, which should place the rows for flows as a left-hand number, and to prove a trace formula, which gives an expression of the left-shift distribution as contributions of closed orbits, fixed points, etc. So we got the left-shift distribution, and we proved that it is equal to the expected distribution of the formula. But we got also some additional distribution we call C. And C shows up by the use of auxiliary tools, which is Riemannian metric and analytic tools. And it is mainly given by some Zeta invariant, which is what I'm going to talk about. And this Zeta invariant depends on a closed one form. And we can change the closed one form within its cohomology class, so we have some freedom. Also, we can change the metric. And then this C, this distribution, indeed, it is not easy to see that it is well defined, and we would like to use the freedom we have to make it vanish. So those are the goals. Okay. To describe this distribution of this Zeta invariant, I have to recall the Witten's perturbation of the RAM complex. So M is a closed manifold of dimension n, and we consider the RAM complex with coefficients in complex numbers. Eta is a real one form which is closed, and it defines a class I call psi. And the Witten's perturbation is given by the RAM operator plus multiplication by eta, which with a coefficient, a complex number, C. So we get twisted cohomology, denoted by H sub 3. Okay. Well, and this twisted cohomology depends on the parameter C and the class psi. And the class vanishes if and only if the cohomology, the twisted cohomology is isomorphic.
Perhaps microphone is not on.
Is your microphone working?
Mute up.
Do you know how to do it?
Wyciszenie menu.
No battery. You can use this one. Yes.
Okay.
Battery is on.
Change. Okay, now it's better. And we have twisted Betty numbers denoted by
Another battery.
okay, so we have these twisted Betty numbers, and they are independent of the parameter C, except on a discrete subset of some vertical strip, which is the real part of the absolute, the modulus of the real part of theta, less or equal than C. And in this discrete subset, the Betty numbers, the twisted Betty numbers may jump. But then we have the other values, which are the ground values, and they are called Novikov numbers. Now we take a Riemannian metric, then we have the corresponding Hilbert space of L2 forms, and we take the adjoint denoted by delta, the adjoint of the Durand differential, minus the adjoint of the stereo product denoted in this way. We have the usual Laplacian, and we have the Witten's perturbations of the codifferential and the Laplacian. If I want to indicate the degree, it is indicated in this way, with summing the degree. And this twisted Laplacian is positive definite, self-adjoint elliptic operator. It is not holomorphic because the twisted codifferential involves the conjugate of the parameter. And but it is analytic on the real part of the parameter and the imaginary part of the parameter, separate. And the eigenvalues are denoted in this way by lambda zeta k k. And we have corresponding orthonormal eigenforms. And the Wales law states this asymptotic expression that they grow like up to a constant like j to the 2 over the dimension as j goes to infinity. Okay. And for a bounded function, we can define the bounded operator or the function of the Laplacian for that degree, which on each eigenspace is like multiplication by the function evaluated on the eigenvalue, on the corresponding eigenvalue. If the function decreases like lambda to the minus n, which with n greater than half of the dimension, then the wave formula, the above wave formula, gives that the function of the Laplacian is of trace class, and the trace is just the sum of the function evaluated on the eigenvalue. And we also have the supertrace, which is the sum of alternate sum of the traces of the function of the Laplacian on each degree. For example, we have the hit operator, which is this function of the Laplacian, here of the twisted Laplacian. And we also have this, we will use this other operator. We take the Laplacian, but only on the image of the, on its image, which is mapped to itself. On the orthogonal complement, it is 0. I denote it with delta prime, so C. And then we can take its power to minus a complex number with a real part greater than half of the dimension, and then this is also traceable. Okay, now the theta invariant. The theta function, we consider this theta function, which is a function of a complex number S and the parameter C. And it is the meromorphic extension to the whole complex plane of this holomorphic function, which is given by the above power of delta prime c, composed with, well, the power is to the minus the complex number s, composed with the twisted codifferential, and then multiplied by the 1/4 eta, close 1/4. And so this preserves the degree, because the codifferential decreases the degree by 1, and multiplication by eta increases it again. And we take the super trace, but this is only defined in this way when the real part of S is greater than half of the dimension. And it, by the general theory of theta functions of operators, this meromorphic function may have poles, simple poles, at the points S written here, which are half integers and integers which are less or equal than half of the dimension. And the Zeta invariant we want to consider is the value of this Zeta function at 1, at S equal to 1, if it is defined, because 1 is in the list of possible poles. In particular, this value of the theta function at 1 is never given by the above expression, because this, if we take the expression, then it turns out to be the inverse of the twisted differential composed with the product by the one form, and this is never of trace class, except on trivial cases. Now the theorem we prove is that if the dimension is even for any class, real cohomology class of degree 1, and for any given number, real number tau, we can choose a metric G and a representative eta of the class such that if the real part of the parameter theta is large enough, well, the absolute value is large enough, then the theta function is smooth away from the half integers and integers which are less or equal than 1/2. So we reduce the possible poles. So in particular, it is defined at S equal to 1. So our theta invariant is defined. And moreover, it is given as a limit of the super trace of this operator, where we have added to the expression the hit operator defined by the twisted Laplacian. And this hit operator, as t goes to 0, in this limit, then it goes weakly through the identity, so it is kind of a renormalized version of the above expression which was not defined. And moreover, the value can be the of the theta invariant can be at the limit when the real part of the parameter goes to infinity, uniformly on the imaginary part, can be the given tau. We can prescribe the value, and this is so for any parameter c, it is tau plus something of order, this expression which goes to c. So in the trace formula, we can choose eta and the metric so that the distribution c is well defined, and moreover we can get that it vanishes taking tau equal to c. So this is the purpose of this theorem. And we don't know any other application, but the proof has some interesting path through mathematics, so I'm going to talk about the proof. In particular, the forms eta we choose in any class are Morse forms, so that's the reason this is an invariant of Morse forms. So let's see let's talk about Morse forms. One form is a Morse form if it is locally the differential of a local Morse function. In particular, it is closed. Globally, it may not be exact, but locally it's the differential of a local Morse function. Then we get that the zero set of this form is finite, and I denote with in this way the zero set of the points where the most degree is k. I denote zero set k. And using Morse coordinates around 0 point of degree k, then we have this expression for the form, which is just taking the differential of the standard expression of a Morse function around 0 point degree k. And we can suppose that the metric is a standard, which means that in flat Euclidean coordinates, it is flat Euclidean with respect to Morse coordinates around the 0 points. So we have this expression around the 0 points. Okay. Now, with these assumptions, if the form is a Morse form and the metric is a standard, then the spectrum splits into two parts. One part which is an interval whose top point goes to 0 exponentially with respect to the real part of the parameter C, and the other part grows linearly. The bottom grows linearly as the real part of the parameter goes to infinity. This was proved by Witten, by Helferes, Hostram, and by Bismuth Tan when the parameter is real, and we just give an extension of their arguments. So we have a small spectrum and a large spectrum, which is the part contained on each of these intervals. And so we also talk of small and large eigenforms and small and large subspaces generated by the corresponding eigenforms. The dimension of the small subspace is equal to the number of zeros, and for degree k, it's equal to the number of zeros of degree k, when the real part of the parameter is great enough. If the restrictions to the small and large subspace of the above operators is denoted in this way, and the Hodge decomposition for this twisted complex is can be refined in this way, taking Hodge decomposition for the small complex, which is finite dimensional, and then a Hodge decomposition for the large complex, which does not have zero kernel of the twisted Laplacian because all the eigenvalues are positive. Okay, and we have that the twisted cohomology is isomorphic to the kernel of the twisted Laplacian for each degree, and also to the kernel of the small twisted Laplacian. Okay, now if we use only the small or large spectrum in the definition of the theta function, we have a small and a large theta function, another set of theta functions, defined in the same way. And the whole theta function is the sum of both of them. And the small theta function is always holomorphic on the whole complex plane, so it is an entire function because we are using only a finite sum. But then the large theta function has the same simple poles as the whole theta function with the same residues. So we have a small theta invariant, which is this value of the small theta function, always defined, and a large theta invariant, which may not exist a priori. So let me talk about the regularity of the theta function. Now consider the number operator. This is the operator of multiplication by the degree for every form with fifth degree. And there is what is called the theta function, now depending on the parameter c and a complex number s, which is the meromorphic extension of this holomorphic function, defined as above for real s greater than half of the dimension, but changing the expression by using the number operator. This was used before, and has, as before, it has possible simple poles at the half integers and integers smaller or equal than half of the dimension. And then we can also define the small and large theta function, like the case of the theta function. And it was proved by Seeley that this theta function is smooth at s equal to 0. So this is well known. And we indeed proved that the residues of this theta function at all possible poles from 1 to half integers greater or equal to between 1 and half, they are independent of the parameter c. The proof is a consequence of work with Peter Hickey, where we have shown that the first and secondary heat invariants of the twisted Laplacian are independent of the parameters. This uses invariant theory. And then we use that the secondary heat invariants correspond in some sense to the residues of the possible poles of the theta function. This is a consequence of general theory of theta function. So the residues are independent. And now we show this theorem, which relates both functions. S times the large theta function at s plus 1 is the derivative with respect to the parameter of the large theta function. In particular, we have this expression of the value of the large theta function at 1 equal to the derivative with respect to the parameter and with respect to s of the large theta function at s equal to 0. And since these functions are meromorphic, it is enough to prove this equality for where they have an explicit expression when real or part of s is greater than n-half. And then it is reduced to a computation of derivatives with respect to the parameter c of operator depending on this parameter. And we make those computations and we check this equality. As a consequence, we get that the large theta function is smoothed away from the integers and half integers smaller or equal than 1/2, because the residues of the possible poles at of the theta function at the points between 1 and half are independent of the parameter. So the same is true for the large theta function. And since they are independent of the parameter, the derivative with respect to the parameter is 0. And then, so this derivative is regular at those points. And so the large theta function is regular at those points by the above theorem, by the above expression relating both functions. Then, so the theta function is smoothed away from those values of integers and half integers less or equal than 1/2. And when the real part of the parameter is large enough, then it has the desired expression, the stated expression in the theorem. This is true because there is a relation between theta functions and heat operators in the general theory given by Melis transform, and we apply that. Now let's see how are the asymptotics of the first small theta function. Okay. So take a small form, eta, and suppose that the metric is a standard. So we are going to use vector fields following the work of Stephen Smith. So take a vector field with flow denoted in this way, phi t. It is said that the vector field is gradient-like if it is minus the gradient of some function with respect to some metric, no matter which function or which metric. It is said that the vector field is Lyapunov with respect to the form if the evaluation of the form of the vector field is negative on the complement of the 0 points. And it is said that the vector field is a standard if around the 0 points it's given in this way, by it's minus the metric evaluated on the vector field. And now we have the stable and unstable submanifolds of the vector field, which are given by the points which at each 0, which is given by the points which converge to that 0 as the time goes to plus infinity or minus infinity. And the dimension of these manifolds, these submanifolds, are the degree in the case of the unstable one, and the dimension minus the degree in the case of the stable one. And it is said that the vector field is small if the unstable and stable submanifolds are transverse for all pairs of 0 points. And these conditions can be assumed, they are generic. We can always find a vector field and a metric satisfying this. For instance, here I draw a picture. The left picture is the most typical Morse function, which is given by the high function of these torus embedded in R3, and it has the critical points where the tangent plane is horizontal, those 4 points. And you see that for Q, the stable manifold agrees with the unstable submanifold of the critical point P. So they don't. This most typical Morse function does not satisfy the Smith condition. Well, I'm taking the gradient of minus the gradient of the function as vector field. So, but if we tilt it a bit, then the situation is like in the next drawing, and then you see that the Smith vector field, the Smith condition is satisfied, because now all stable and unstable submanifolds are transverse. Okay. If we take 2 0 points of consecutive degree and we intersect the unstable submanifold of one of them and the stable manifold of the other one, then this intersection is a finite union of trajectories of the flow from P to Q, from the one with larger degree to the one with smaller degree. And these are called instantums. The name was given by Witten, and they are called instantums because they stay next to P, very close to P, almost all the time, and then in one instantum it moves to close to Q and stays close to Q all the time, all the rest of the time. I will denote by T of PQ the set of instantums from P to Q, and we fix an orientation. We fix orientations of the unstable submanifolds, And now we have an integration of the unstable submanifolds of the forms of the degree equal to the dimension. This is not at all clear. It's a strong result proved by Laubenbach, Harvey, Minarini, Burgalea, Friedlander, Kappeler. And for instance, in the last proof given by Burgalea, Friedlander, and Kappeler, it's very illustrative because they construct a manifold with corners which is immersed in the submanifold for every unstable manifold, submanifold, which is a completion of the unstable submanifold, so that the interior is diffeomorphic to the unstable submanifold. So integration on the unstable submanifold is the same as lifting the form to the manifold with corners, and integration on this, and take integration on this compact manifold with corners, like in this situation. Okay, now we prove this theorem that given any real cohomology class of degree 1, we can choose a metric and a representative and a vector field with above conditions such that for any degree and for any zero of that degree k, there is a positive number so that the maximum in the zeros of degree 1 unity less, and taking all instantons from both points, the integrals of the form are equal, the maximum is equal to minus that number, independent of this. In the case of the differential of a Morse function, this was proved by Stephen Smith, and I can use the above. Okay, I can use this to say something about this. In the case of a Morse function, sorry, it means that all flow lines, all instantons from, say, for instance, from Q to the bottom, have the same integral, or the integral of the differential of the function is the same of all those instantons from two fixed points. This can be proved in the case of the differential of a Morse function. But in the case of one forms, which are not exact, this is not true, because otherwise all periods of the form would be zero, because then you can integrate along the closed path formed in this way, and it would be zero. So for one forms which are not closed, we only have this maximum. We can only prove this. But the proof is just an adaptation of the arguments of Smith. Okay, now let me talk about the Morse complex, or a twisted Morse complex. We take the space, the vector space generated by these zeros. Let me read it in this way. And then for each zero, we have an element which has the value 1 at this 0 point and 0 at other 0 points. And there is a differential defined, a twisted differential defined in this way, which maps every the element defined by the 0 point q of degree k minus 1 to this expression. This expression contains the elements defined by 0 points of degree k, and the coefficients are given by the instantons. So we have the exponential of the parameter 3 and the integrals of the form eta along the instanton, and epsilon of gamma is +1 or -1, depending on the chosen orientations of the unstable submanifolds. We can take a metric in this complex so that these elements defined by the 0 points are orthonormal. And then we can also talk about the twisted codifferential and the twisted Laplacian, but this is always in a finite dimensional space because the set of zeros is finite. Okay. We have let me see. Okay, this is the okay. Now if we multiply the differential at the twisted differential at every degree k minus 1 by the exponential of the numbers ak, the above numbers ak times the parameter, when we can decompose it as sum of two operators, one which is independent of the parameter, taking only the instantons which whose integral, so that the integral of the form on that instanton is minus ak. This is reached as a maximum, and the other operator is given by the other instantons. Okay, and you see that by definition we have that the second part is for the decreases exponentially with respect to the real part of the parameter. Then from that we get that the first d prime is defines a complex, and then we have also the codifferential delta prime and Laplacian delta prime. Okay, this is also operators on this finite dimensional space. And the codifferential has a similar expression multiplied by this number. This exponential is the delta prime plus something which decreases exponentially. So we get that from that in this subspace the image of delta plus the image of d with appropriate degrees, then we have that the twisted Laplacian is equal to this exponential times the operator delta prime, which is independent of the parameter, plus some term which decreases exponentially. And so we get this estimate for the spectrum of this twisted Laplacian on the Morse complex. On the subspace, it is the spectrum is contained in this interval. C and C prime are given by the bottom and top of the spectrum of the non-zero spectrum of delta prime, which is independent of the parameter. Okay. And now, I have jumped into one page. Okay, it doesn't matter. Okay, as a consequence, we get this theorem for the spectrum of the twisted Witten Laplacian, the small part of the twisted Laplacian. On this subspace, the image of delta for degree k and the image of d for degree k minus 1 is contained here in this interval that is similar as the above interval, but now we have to add the absolute value of the real part of the parameter multiplying on each the endpoints of the interval. So I have I'm missing one page. Here. There is this theorem that we have the integration on the unstable submanifolds defines a chain map from the Witten's complex to the twisted complex or Morse complex, and so it induces the homology, also a map, and there is a theorem showing that there is something like an inverse, which is almost unitary as the real part of the parameter goes to infinity. The top spread equalities means that this is almost unitary. And the composition of psi and phi is different, is an isomorphism, because these numbers are never zero. The real part of the parameter over pi to the dimension over 4 minus the degree over 2. This number is never zero. And then we have a term, an extra term for the which decreases exponentially. This was proved by Laudenbach, Bismuth and Zhang for real parameter, and we adapted the arguments of Bismuth and Zhang. But there is an additional difficulty, which is what we prove here. This is not very easy to see. When we have a number m greater than half of the dimension, then the L infinity norm on differential forms is less or equal than some constant depending only on m times the Sobolev norm, but the Sobolev norm is defined with the twisted Laplacian with using square root of -1 times the twisted Laplacian for this form. Okay, so this is I like the proof of this implication because it uses differential topology to prove something which is an inequality of norms on functional analysis. Okay, so it has this extra difficulty. And so now for large enough parameter, real part of the parameter, we have an isomorphism. This integration defines an isomorphism between the small subspace and the Morse complex. And in cohomology, we get an isomorphism also in the real part. For real parameter, this was already known. Sorry. Okay, we have seen this, and we have seen this. This was also, this estimation of the small spectrum was also proved by these people, Peltrek, Nier, Vieterbo, and also Michael, when the parameter is real and the form is exact, so for Morse functions. And they use it in quantum mechanics, in physics. Okay. Sorry. Okay, now the asymptotics of the small Zeta invariant is given by this theorem. I use, I denote by M1K the dimension of the image of the small differential on degree K. So it's the small differential defined on degree K minus 1, which is independent of the parameter for large enough real part. And we show that the small theta function evaluated at 1 has this expression, a part which is independent of the parameter, and another part which goes to 0 with this sorbet, depending on the real part. So the real part of the parameter goes to infinity. And to prove this, we use the above-spectrum estimate and some similar arguments, but a little bit different, using the maps phi c and psi c. Now let's see how is the asymptotics of the large Zeta invariant. For that, we have to make some more definitions. the determinant of the Morse complex of the K is, by definition, the top wedge product of that space. So we take the wedge product of the degree equal to the dimension. And we write -1 when we take the adjoint. These are the spaces of dimension 1. And the determinant of this graded space is the tensor product of every degree of the determinant of for every degree to the power -1 to the degree k. So we take the adjoint 1 times, and for the next degree we take the time. And the norm we have in the Morse complex induces a norm in the determinant of the Morse complex, because if you have the orthonormal frame I have defined for the Morse complex, and then if we take tensor products of those frames, of the elements of that frame, we get an element of norm 1 in the determinant. Now, for the cohomology of this twisted Morse complex, we also define the determinant in the same way. And it turns out that there is a canonical identity between the determinant of the twisted cohomology and the determinant of the Morse complex. And now, it's time.
No, you have time, but the microphone.
Change. Where is the second microphone?
Maybe you use this one. Try with this one.
Thank you. So, using this identity, the norm we have in the determinant of the Morse complex defines norm in the determinant of the twisted cohomology of the Morse complex. On the other hand, on the kernel of the twisted Laplacian of the Morse complex, we have the norm, the restriction of the norm, and this, by the Hodge isomorphism, is isomorphic to also to the twisted cohomology. So we get another norm, which I denoted only with one vertical line. And this is different. Indeed, they are related in this way by the theta function defined in the same way as before for this Morse complex. So the determinant I have defined first is equal to the norm of the determinant I have defined first is equal to the norm to the second norm times the exponential of the derivative with respect to s of the theta function on s equal to 0 divided by 2. This can be proved. And also, the cohomology, the twisted cohomology of the manifold is isomorphic, as I said before, using the map defined by phi c to the twisted cohomology of the Morse complex. And so, this norm corresponds to another norm on the determinant of the twisted cohomology, which is called the mean-norm metric. This is the definition of the mean-norm metric. Okay, so now we can take all the whole forms and try to define also in a similar way a metric on the determinant of the rank complex, but the determinant of the rank complex is not defined because it is of infinite dimension. So we take the second procedure and we take the L2 norm on the kernel of the twisted Laplacian, which is isomorphic to the twisted cohomology by the Hodge isomorphism. And so we have the corresponding metric or norm on the determinant of the cohomology. The determinant of this twisted cohomology is well defined because it is of finite dimension. So we have this second norm only. And the first norm can be defined now using the above formula for the theta function I have defined before with the theta function. This is the only way to define it because we don't have a norm, we don't have determinant of the rank. And this is called the Reisinger metric, or also called Quillen metric because Quillen has used this before. Now, Miller and Jigger has shown that this Reisinger metric and the Morse metric are equal, the determinant of the twisted cohomology, if the parameter is imaginary. This is a particular case of a more general result, but in our case of this Williams perturbation, it's just when the parameter is imaginary. In general, we have a more and more formula, which was proved by Smoot and Sam, which is this theorem. Let me explain it. We take the zero section on the tangent bundle, and then there is a current on the tangent bundle, which is denoted by psi, which is called Mattei-Quillen current, which is locally integrable and of degree n-1. And on the complement of the zero section is equal to minus the angular form. And now, since x is traversed to the zero section, because this is the same as saying that its 0 points are simple, then we can take the pullback of this current to m. And on the other hand, we also use that x is gradient-like, so it is minus the gradient of some function h with respect to some metric d prime. It doesn't matter which metric. And then the Smoot and Sam have proved that the quotient between the Reisinger metric and the Milnor metric has a logarithm equal to this integral. Here we have, is the product minus the integral of the product of the differential of s minus the real part of the parameter c times the form, which the pullback of the current of degree minus. Okay, so this is well defined. And so both metrics are equal when this logarithm is 0. So here we have exactly what is needed for this logarithm to be 0, this integral. We use this. This is a very strong result. It took, the publication has about more than 200 pages. And it's a very famous result in global analysis. Sorry for Okay, now our theorem about the asymptotics of the large theta invariant states that with our choice of the representative theta of the class psi and our choice of the metric, then the large theta invariant is equal to this integral, the product of the one form eta plus the pullback of the current psi, and plus some term which is which goes to 0 with this order as the real part of the parameter goes to infinity. Let me tell something about the proof. By the theorem of Smoot and Sam, if we take the derivative of the logarithm of the quotient of the norms of Reisinger norm and the Morse norm, then we have the derivative of the integral. The derivative of this, and this integral turns out to be 1/2 of eta times the pullback of the current, which is instead the sine 1/2 what we have written there. And now we define a small Reisinger norm on the determinant using only the small theta invariant, the small theta, the value of the small theta function at 0, and the derivative with respect to s at before and 1/2. We define this, and now we can write the logarithm of the quotient of the Reisinger norm and the Milnor norm as the logarithm of the small, the same quotient, but taking only the small Reisinger norm, and then there is this expression using the derivative with respect to s of the large theta function at 0, and then we take the derivative with respect to the parameter c, and it turns out to be the derivative of the first logarithm, and in the second part we have the derivative, but this derivative, these two derivatives are just the large theta function at its value at 1. And now what remains is to prove that this term, this quotient, has ordered the absolute value of the real part of the parameter to the minus 1/2. And this is difficult to prove, but it's very technical, many computations to do. Okay, so now it's almost everything done because, okay, now we sum the two expressions, the two asymptotic expressions, and we can choose what we have the A case and all other choices we have made, so that we can get any given tau, any prescription for the limit with appropriate choices. So this finishes the proof of the theorem, and thank you very much for your attention.
Okay, thank you for your talk. Now it's time for questions and comments, please. Everything was clear.
I am not expert in this subject, but I have such a question. Have this twisted cohomology some geometrical meaning? They are connected with ordinary cohomology?
Okay. Yes. If the form is exact, the differential of the Morse form, then it was used by Witten to show Morse inequalities and to prove it has also moral consequences in quantum mechanics. Yeah. The way he proves the Morse inequalities is, in that case, the cohomology doesn't change because it is isomorphic to the usual cohomology. And then, but then this is good because then you can use the perturbation of the Laplacian to represent the same cohomology, but to take the limit as the parameter goes to infinity and see how is the asymptotics. And then the asymptotics of the corresponding harmonic forms concentrate around the critical points, and then you can see that you get the Morse inequalities in an analytic way. And okay, for a general form, Novikov and other people have generalized this, and it is much more involved. It is related with other things, yes. But it's a whole theory. It can be, there are several ways to look at it. A very algebraic way, and there are also an analytic. There is also an analytic way. So Bismuth and Fang have written much about this. It's an important reform, and they have developed it very much. Now it's what is called the well, I don't remember the name. Okay, there is a big development about this.
No questions, no comments? So if not, we thank the speaker again. And now I leave the microphone to the panel. The only one. Last.
Ladies and gentlemen, before the lecture of Paweł Walczak, we come back to the opening ceremony in a sense, and would like to have a small ending the honorary membership to Professor Paweł Walczak, and I ask now the Maciej Czarnecki to say a few words about Professor Paweł Walczak.
Okay, thank you very much. I have a great pleasure to introduce Paweł Walczak in the occasion of giving him honorary membership of the Polish Mathematical Society. I think that this few facts from his life and career makes obvious that he is a great mathematician and very and very engaged in the actions of the Polish Mathematical Society. Professor Paweł Walczak was born in Łódź in 1948, obtained his master in mathematics at the University of Łódź, PhD at the Institute of Mathematics of the Polish Academy of Sciences in 1974, then habilitation and the title of professor in 1992. He's an author or co-author of over 90 research papers, published, for example, in such distinguished journal as Acta Mathematica, Mathematyczna Annalen, Geometria Dedicata. He also wrote 3 monographs, among them the most recent. The most recent about extrinsic geometry of foliation together with Władimir Romeński. Paweł Walczak is working mainly in the field of foliation in any aspect of the foliation, geometric aspect, dynamical, topological, and any other. And he is the person who knows many aspects of the contemporary mathematics, not only geometry and topology. Let me mention that Paweł Walczak was the head of the Department of Geometry at the University of Łódź, and now still is a professor, and this head of the Department of Geometry for 32 years. Among others, he was a director of the Institute of Mathematics, and some scientific activities concentrated on the conferences, maybe on the cycle of the conferences of foliations for over 1/4 of the century. Our laureate was the visiting professor at the universities of St. Louis, Tokyo, Dijon, and has 11 PhD students. Sorry, and now something about actions for the Polish Mathematical Society. From 2005 up to 2011, he was a vice president of the Polish Mathematical Society. Before was the president of the Łódź branch of the Polish Mathematical Society. Obviously not to 2024, 2004. For many years, he was head and member from time to time of the PTM prizes jury and the head of the Polish Mathematical Olympiad. As you probably know, it is obvious for everybody. He is the head of the program committee of our meetings, the Spanish Polish Mathematical meeting. Let me say some fact which is not on the slides, that Paweł Walczak is a very kind person, interested in all the mathematics, and his students has a possibility to learn mathematics from the person which is really interested in it. So it is not so frequent. He's also head. Sorry. His wife Zofia is here co-head of the mathematical family. Parents and children are mathematicians and work in mathematics for applications. I think he deserves it all for this honorary membership of the Polish Mathematical Society.
Congratulations and thank you for all your work in the field of Polish Mathematical Society, but also for Dziękuję bardzo i jeszcze raz.
Dziękuję bardzo. To jest dla mnie, tak? Tak, dziękuję bardzo. Dziękuję bardzo. Jeżeli pan coś chce powiedzieć, to... Probably I should say more words about all of that, but looking at the watch, at the clock, I can see that the time of lunch approaches, not immediately, because first I have to talk for a while. So I would just reduce my talk, let's say, about this document, saying thank you.
Lunch can wait.
Thank you. Ooh, then it becomes cold, and it's not so healthy. So I will reduce my talk to few words, saying thank you to everybody who was involved in this let's say story, and thank you to all of you all of the members of the scientific committee of this meeting who worked together with me some years ago, because before the first official planned date of this meeting. So it was something like 2019, maybe 2020 also. So thank you also thank you to everybody.
this is going to work. I don't know.
Another one here, but the battery is on. No, this one is here. Do we have another microphone? Because we can write this one. But I don't know how long it.
No, how does it work?
Yes, you can shoot me.
No?
Is this working? Yes. Okay, so it's a pleasure to introduce the talk by Professor Walczak entitled Geometric Flow.
Thank you very much. First of all, I would like to express my thanks to the organizing committee for inviting me to speak. It's not scientific committee, this is organizing committee who invited me. So, this will be a relatively short lecture about geometric flows. You can see a flow of a river here. The river is called Inn. It's a picture taken in Switzerland, and in the buildings on the right, from my point of view on the right, there is a museum of contemporary art established some 10, maybe less than 10 years ago by some Polish specialists of art. So the place is called Zusz, S-U-S-H-S-C-H, and it's located in Switzerland, as I said. Okay, so this is about the page, the first page, and now,
You have to point that address to the computer.
No.
You want to take over.
Maybe I'm in the wrong position. It worked. Oh,
No, it won't.
okay, now it works. Okay, so this lecture is about Riemannian geometry, in fact. So we have a compact, usually compact, but at some points it's not important, Riemannian manifold. That is a manifold equipped with a Riemannian structure denoted by G. Manifold is denoted by M. And for those of you who are not familiar, I would say that this Riemannian structure assigns to any point of a manifold a scalar product in the tangent space. The scalar product should depend smoothly on the point of the manifold. And now, by definition of today, a geometric flow is a family of Riemannian structures satisfying some equation. The family should be somehow smooth with respect to the parameter t, and the equation is the derivative of this family. E should be of the form f, well, f is a reasonable function, a function which assigns to any Riemannian structure on M a symmetric tensor of the same type as a Riemannian structure. This means of type 0,2. This terminology means that the structure assigns a real number to any pair of vectors tangent to M at the same point. Now this function should be reasonable in some sense. So geometric. Now I think I changed this notation f to q. I didn't notice that. Okay. Well, anyway, geometric invariants on a Riemannian manifold are some quantities which could be scalars, vectors, tensors, etc., depending in a rational way on G. In a rational way means that if you have an isometry, then these somehow quantities should be the same in the sense that one of them arises from the other one, by a suitable map arising from F, which means suitable means sometimes differential, sometimes co-differential, sometimes built of differential and co-differential in a way, in a needed way. As you know from probably time of our studies at the university, differential geometry of surfaces splits into intrinsic and extrinsic. The same happens to Riemann geometry. In this case of surfaces, let's say surfaces in R3, intrinsic geometry arises from the first fundamental form. And here means arises from G itself, and extrinsic arises from the first and second fundamental form. This extrinsic geometry makes sense if our manifold is immersed in another manifold, or it's equipped with some extra structures, which usually looks like a plane field. Plane field means that this is a function which assigns to any point of a manifold a subspace, linear subspace of the tangent space, and usually we assume that this is, again, depends mostly on the point, and in particular, all these subspaces are of the same dimension. Sometimes, well, this plane field can be integrable or not. Integrable means that at any point you have.
The battery is over.
Thank you, dziękuję. At any point you have a submanifold of the dimension equal to the dimension of the plane field, which is tangent to this plane field. There exists also non-integrable plane fields, as you probably, at least some of us know. Okay, so in this story, our plane field can be either integrable or not. So therefore, geometric invariants are of these two types, intrinsic and extrinsic. The important intrinsic invariants come from the Levi-Civita connection and via the Riemann curvature tensor R and its contractions, Ricci curvature or scalar curvature. Curvature tensor, let's say, of a Riemannian manifold can be seen as a tensor field of type 0 form. Therefore, you can contract it twice. If you contract once, you get Ricci. If you contract twice, you get scalar curvature. Contracting means taking cases. Now, these extrinsic geometric flows or extrinsic geometric invariants are determined by the second fundamental form and the corresponding shape, sometimes called Weinberg operator, of either a submanifold M of another manifold M bar, or a plane field D defined on R. In the case of a plane field, one can think also about geometric invariants of mixed type. This means you can mix intrinsic and extrinsic invariants, producing something new, producing something new. Okay. We can do that. What happens? Nothing happens.
Stronę komputera.
Okay. Thank you very much. I should do that. I should forget about this, maybe. Okay. The most classical intrinsic geometric flow is the one called Ricci flow, and probably everybody here could had a chance to hear about it. This is the geometric flow arises from this function capital F, which is up to a constant, coincides with the Ricci tensor of a given manifold. So f of g is just minus twice the constant plays some role, but okay, forget it. Which means minus 2 times the trace of the remaining curvature tensor trace with respect to the second and third argument. Why is it important? I can tell you on the next, I can explain it on the next slides. But anyway, the first question is always, this looks like this equality, f of g equals r min. The differential of gt over dt equal to capital F of gt. This looks like a system of partial differential equations. Therefore, as usual in the theory of differential equations, the first question is about existence and uniqueness of solutions. And in this case, we have positive answer. This means that for any closed invariant, closed means compact without boundary, closed remaining manifold, there exists a unique solution to the Ricci flow satisfying a given initial condition G0. So starting from any remaining structure, you get a family of remaining structures defined in a neighborhood of 0, satisfying this equation. Then it can be proved more. There exists maximal value of the parameter epsilon in the first theorem for which the solution exists, and sometimes this parameter, capital T can be finite or not, and it's finite if and only if the curvature of the manifold, the curvatures in fact, the curvatures of the manifold expand to infinity with T. I mean the kind of subnorm of the norm, the subnorm of the norm, sum of the norm of the remaining curvature tensor for these solutions GT, for these structures GT should escape to infinity, then T is finite. Otherwise, T is infinite, therefore there exists global solution defined from 0 to infinity. And I think I can do this. Thank you very much. Now, this is why the Ricci flow is important. Why it is really important. That is, there existed conjecture by Poincaré asking if any simple connected closed manifold of dimension 3 is diffeomorphic, or maybe even homomorphic, but diffeomorphic to the round sphere. And this was somehow solved step by step, and people involved in this story are Hamilton and Perelman. And finally, it is proved that using this Ricci curvature flow, a Ricci curvature flow, like Ricci flow, that indeed the conjecture is true. Every closed remaining manifold is diffeomorphic to the round sphere. And this was somehow completed by Perelman in, I think, the pair of 3 of preprints, which are never published due to some I would say psychological problems between the author and the editorial committee of one of the most prominent journals. But anyway, many people verified these preprints and declared that the result is correct. So this Ricci flow was used to to prove one of the most famous curvatures conjectures in the history of contemporary, more or less contemporary mathematics. There exist more intrinsic geometric flows. For example, Keller-Ritchie, which is the complex analog of the Ritchie, something called Yamabe flow, which arises from some invariants produced again from scalar curvature, and so on and so on. So this is about intrinsic, and now I would like to switch to extrinsic geometry. So the motivation for what I will speak about later is the following result, some, let's say, approximately 40 years old, which is a kind of very, I would say, simple but not trivial, of course, observation that if you consider the equation like that, you consider one parameter family of planar curves. The planar curves are denoted by Ct, such that the variation field dc over dt is parallel to the normal, to the unit normal, the vectors, unit vectors orthogonal to the curves, and parallel with a coefficient which is just the curvature of the curve. Then these curves, if you start from anything, in fact, for any smooth, simple, closed planar curves, that under this variation, let's say, it stays all the time smooth and simple, and finally it becomes convex, and as soon as it becomes convex, then shrinks, in fact, to a point, and it becomes more and more similar to a circle, and finally shrinks to a point. This is motivation for our maybe it's too early to say our. Now, something slightly more general is a similar consideration for surfaces and let's say hypersurfaces in the Euclidean space of arbitrary dimension, and mean curvature replacing the curvature of the curve of the previous slide. Now we consider the similar situation. We have a given hypersurface, a given in fact manifold, and this manifold is immersed in the space of dimension n+1. And we say that the family of immersions like that provide mean curvature flow if the equation, the evolution equation, similar to the previous one, is satisfied, where HT here means the mean curvature of the embedded hypersurface. Mean curvature is just the trace of the second fundamental form, or if you like, the trace of the shape of Weingarten operator. Then again, similarly to the case of curves, similarly but not exactly in the same way, we have some tolerance produced by different authors, but finally, well, I think the best reference for that is the book called Just Geometric Flows by Cao and Yao. Well, the result is that if you start from any closed hypersurface which satisfies some conditions of convexity, which means that the eigenvalues of its second fundamental form are strictly positive everywhere, strictly positive. This uniformly means that strictly positive and bounded in a reasonable in bound. Then the equation from the previous slide has again a smooth solution of a finite time interval and from 0 to capital T, and then the images under this emergence of T converge to a single point as T, as small t, parameter T converges to this capital T. There exist many generalizations of this result. This was about dimension 1. I mean that my manifold n was of dimension n, was immersed in Rn plus 1. But there exist many generalizations for codimension bigger than 1, n being immersed in an arbitrary manifold, maybe not, okay, arbitrary in particular in the spheres, in the sphere or in the hyperbolic space, and so on and so on. Okay, finally, we, that means Professor Rowensky and myself, we studied something like this extrinsic geometric flows on a manifold equipped with a foliation, or with a non-integrable plane field, but here I reduced to the simplest case of foliation of codimension 1. Foliation of codimension 1 means just that you have a manifold filled with submanifolds of dimension less by 1 and located nicely in the whole space. Located nicely means that locally this family of submanifold called leaves looks like sheets in the pack of paper for printer. Okay, so notation like is here like that we have a manifold closed, foliated, I mean equipped with a foliation of codimension 1, and everything is assumed to be oriented. Therefore, we can choose a positively oriented, in some sense, unit vector field orthogonal to the leaves, to F means to the leaves. Then we can define the second fundamental form of F in the way analogous to the second fundamental form of a single submanifold or a single surface in R3. Then we can define corresponding shape operator. Definition is here. H is just, how to say, H and A are somehow related via the remaining structure. And then, since A is a linear endomorphism of the tangent bundle, of the bundle of vectors tangent to the leaves, we can iterate this. So we can define the power A to the power n, we can define A to the power A to n, and then we can define also the corresponding symmetric, in fact, to form Hn. Then we can consider vector of, how to say, higher mean curvature, that is elementary symmetric functions of principal curvatures of the leaves. Principal curvatures means just the eigenvalues of the shape operator. And then we can, using all these objects, we can define this quantity Q, which depends on G, also depends on G and F, which is defined in the last line. That is, we consider a function, we consider an arbitrary function Fm. We apply this to the vector of these principal curvatures, multiply by this form Hm, we sum over M. Usually we sum over M in a reasonable finite domain, not from, let's say, from 0 to infinity, but let's say the sum is finite. Then, under some natural conditions for the original structure, I mean G0 and F, the solution of this, or here it's written, the derivative is written in a different way than in the first slide. But anyway, the derivative of gt over dt, the extrinsic geometric flow is defined by the equation dgt over dt equal to q over gt, has a unique smooth solution defined locally in a neighborhood of 0, and then in some particular cases, which is in the second term, particular cases like that instead of this q of gt, or in place of this q of gt, we take the Lie derivative, this L denotes the Lie derivative in the direction normal to the foliation of this family of second fundamental forms. Okay, anyway, this flow has a unique global solutions for all t, for all non-negative. Okay. Now this solution converges to a smooth Riemannian metric called here G infinity, for which the mean curvature of F vanishes identically. Here I didn't say, I said that if the normal structure of this foliation is reasonable, I mean if trajectories of this unique normal vector field form a vibration. In general, there exist foliations for which Riemannian metric satisfying the condition of the theorem, I mean with vanishing mean curvature, there exist foliations for which there exist no Riemannian structures making the mean curvature vanishing. And well, there is no blackboard here, maybe so I should show you like this, like that. If you have a domain, oh no, forget. This is easier. So if you have a foliated domain means just the union of leaves, foliated domain bounded by family of leaves, such that the transverse orientation is always either always inwards or always outwards. I mean, along all the boundary. The boundary could consist of several leaves, and along each of these components of the boundary, the orientation should be the same. If a domain like that exists, then we can say, or there is a terminology saying that the foliation is not geometrically taught. This means that there exists no Riemannian metric with vanishing mean curvature. I think that's almost all. That's almost all. Okay, so just I wanted to say that there exist more results in the book I cited somewhere before. There exist more results about that, and thank you for your attention. I would say smacznego, which means bon appetit, or something like that in Polish.
Okay, what else working again? Before eating, we have time for questions.
So it would be rather common. So there is a community which is called mathematical relativity, which is between, let's say, Einstein equations and math. And I don't remember exact dates, but among those flows, there was an important flow which is called inverse mean curvature flow.
That's right.
And in fact, this gauge, physicists say gauge, was proposed firstly by Geroch, and Hiske-Nillman and proved under some general conditions that such a foliation, it is not exactly foliation, but nevertheless it has well properties with respect to this parameter, and because of that, they managed to prove so-called positivity mass field, Riemannian case. And I just want to announce that these applications were very crucial also in this topic. Okay.
This one has got reagents. Some more questions or comments?
So I would like to ask about the second theorem that you saw in your last slide. Well, not actually the last, but almost the last slide.
Last one. Okay. I mean, last one, but one way.
The
Here. No.
next one, yeah.
Here.
Yeah, so if I understood correctly, this limit, the infinity, is the metric on the of the whole foliation, right?
This is the metric on M, on the manifold.
Aha, and all the leaves are minimal.
All the leaves are minimal.
And can you tell if this limit or this foliation in the limit is going to be, the leaves are going to be equidistant? Or
I'm afraid not. I'm afraid I cannot tell you.
Okay.
No.
Okay, thank you.
No, I think in general, I believe that in general not, but I'm not sure.
Okay, more comments or questions, please? Well, if not, we thank Professor Walczak again. Thank you very much. There's another one for
Okay.
I don't know.
It's late for coming.